Oh, USB-C or? Oh, I can just put it over here. USB-C, the new awful standard. Okay, are we? So many things. All right.
I have to watch some sort of like avatar film before I can see your Twitch screen.
Yes.
Arc.
Sorry.
Yeah, that's the problem with non-partnership streams, is that it'll by default run ads.
Yeah. Okay. Looks good here. I mean, we're on the same Wi-Fi network, but
All right.
I can see it.
Let's do it. Question is, can you still see it after I press the play button? Or can I press? No, that's not the play button. That's just a trick. All right. Great. Can you still see it? Because I can't see the stream anymore.
Just there's a lag on the stream itself, but that's
it's 20 seconds, yeah.
Things like Twitch, so
all right.
It's about 30 seconds behind.
Okay, sounds good. All right, so I'm going to be talking a little bit more concretely about the Bayesian force fields. We have a little bit of time for this, so please jump in and ask questions, and we can work on the board if we need to. That's right. All right. So why we need, or we first have to think about what we want in a force field parameterization approach before we can decide that a Bayesian approach is actually sensible. And one of the most important things is that, as David highlighted, we have to do things where everything is automatic. We don't want to hand fit anything, which is a departure from how things have traditionally been, especially the feats of chemical insight are manual exercises of extremely skilled labor that have guided things like atom type selection and functional form selection. We would like to get rid of that and have the data really drive these choices, especially when it comes to determining how many parameters we need. And it would be great if we could select appropriate functional forms and atom types as well, which we'll hear more about later today. And if we can systematically improve force fields with more data by using the same consistent way of parameterizing things. Right now, as you've seen from David, he tweaked things based upon using some dielectric data, but it was really a tweak correction after the fact. It's not really systematically incorporating that data into the same framework that Jim Mai used to parameterize GAF. And then it would be great, and what's really missing in our field, especially in terms of prediction, is having an assessment of how reliable all of our predictions are. And that's something that's never been done before in our field in any sort of useful manner. And for us, just conveniently, because we have a limited amount of resources, it would be great if we could figure out what data we need to collect to actually make things better and balance the cost versus the information gain or the benefit. And the Bayesian approach really does fit all of these needs. So,
John, I have a question.
Yes,
So
go for it.
The application that you're using has to be part of the data that you put in, the empirical data, right?
The fundamental a concept in machine learning is that your training set and test sets have to come from the same distribution, right?
If you're using liquid density data, all that, and you're applying it to binding, right? How do you know that the uncertainties that you're estimating on a new domain are actually meaningful?
So again, in machine learning, the whole idea is that if you're thinking of, have a black box that has parameters, I'm trying to train some function, the test and training sets have to come from the same distribution in principle. So that means that if you want to do binding free energies with proteins, in principle, you'd have to train on binding free energies in proteins. On the other hand, those are so computationally costly and we feel that these force fields, that they're fundamentally meant to be transferable. So we think you could think of it sort of as a multitask or task transfer learning in that sense. We're learning on one task that's very easy for us to verify, and then we're trying to transfer that to another task.
But there's very little evidence that's transferable.
Possibly. So in certain domains, we think that there is a lot that's transferable. That's a hypothesis that we can test. But we can do that by partitioning data to have some actual validation data that we can assess outside of that. We can verify if the confidence intervals are accurate. There's very nice ways, actually, of making sure, like these QQ plots, to make sure that if I say this is a 95% confidence interval, 95% of the time the predictions should fall within that confidence or the posterior predictive interval, right?
Another important physical thing we're doing is trying to pull as much as possible from mixture data set, the properties of mixtures rather than pure liquid properties. Because if you have optimal involved with water in that, you get the notes, and look at the changes that occur within that much closer to protein ligand binding.
I'm just going to go to this plot here. So
could I also just say, I think what's important here is also, this is a physics-based method. And in fact, all us people who believe in physics-based methods, we have this faith that if we get the physics right, then it should be transferable into new domains. We've come to accept this about quantum mechanics. does that seem
Well, I
to be
mean,
very
you could
powerful?
end up over-parameterizing in the current domain, but in the new domain,
Right.
you're
Should-
in the space.
But we have seen some consequences of this, even if they aren't perfect. So we can come up with some of our methods for some of the charge models that we've come up with have shown transferability into new domains. So we have some basis for believing that it should be able to happen. So this is where we would expect to depart from the pure machine learning in a non-physical way, where if you don't train on the same domain, you can't expect to get it right. It's because we're physics-based that we believe that we should or we might.
There's also a statistical way to think about this too. If we did believe that our hypothesis space was big enough to capture the true potential energy surface of nature, right? Any information we get is useful information and will reduce our uncertainty to the point that it makes our posterior distribution more peaked, right? Even if you're collecting data from a completely different kind of experiment, like a different liquid phase, as long as the model space is big enough to have something that can go between all of those phases, as long as we train on something that has information content, it's going to reduce our parameter uncertainty and make predictions more accurate. So that's the fundamental idea here. Now, obviously, we can't have the true model space. So the question is how we deal with that, and that's an actual technical question we're going to have to come back to. So, why Bayesian specifically also is that it solves a bunch of the other problems that we'd run into in force field parameterization. When I was hanging out in the Coleman group in 1999, Jume was putting the finishing touches on GAF1 and found that essentially there's this whole swath of parameter space that's equally fits the data. And this is a general feature of any kind of nonlinear parameter optimization where you can change individually one parameter at a time and find it really destroys your fit to the function. But you can change all the parameters at the same time along this weird banana-shaped hyperspace, and you can get extraordinarily good fits to all of the data. So what do? Do you just pick something in the center? Well, in the Bayesian approach, it says all of these solutions are equally good, so we should use all of those because we don't know what the impact is on whatever you want to predict down the line. We really need a good way to assess the systematic error, and it's misspelled required, but we'd like to make sure these decisions are really driven by a statistically sound methodology about how many parameters we need. And we definitely need domain and chemistry specific assessments of systematic error. Mike Gilson at one point had suggested, why can't we just do some large-scale benchmarking and then use the benchmark error on a domain of things? But we can only subdivide the amount of data we have so much, and we can't really say at the level of sulfonyls or sulfonamides are causing a particular problem in the context of some other chemical group, unless we have all of those interactions expressed in the force field in some way. But we can do that with these Bayesian methods. We can get a per-problem prediction of what our uncertainty is arising from the parameter uncertainty of how it was trained.
And I guess, this is something we've talked about a lot, and I guess one thing that I'd be curious about, maybe it's just it risks being a side project that somebody, was like, why don't we just work on the main thing? But it seems like these concepts are testable. We talked a long time about making toy systems to test whether the Bayesian thing behaves the way we want it to behave.
And we should definitely have anything that's a small discrete project can easily be done within the context of this collaboration that advances our understanding of how these things behave. Yeah. So we should definitely keep track of those. We want to make data-driven decisions about these functional forms, and the data will tell us which mixing rules we want to use for Leonard Jones. And we can balance the proliferation or rein in the proliferation of parameters, because as you create more parameters, the Bayesian approach penalizes complexity because it's entropically unfavorable. If you have a tiny region of your prior space that you have to hit, and you want to create a new parameter set and it has to be in the same space as that other parameter, you don't gain anything from splitting the parameters that way, and it's entropically disfavored by having to narrow part of your prior space. And then finally, we want to identify which experiments actually give us the most new information at least cost. There's the whole field of Bayesian experimental design that we can use in this case.
So can this also solve, since you have different types of data coming in, right? Current space data, quantum data. Now, does this also figure out which one to weigh more or weigh less?
There is no more weighting involved. It's actually weight-free. So
you have different physics.
You have different physics, and the way that this works is, David has already showed the basic idea that what he didn't mention, by the way, is that one goal for us is to have a single reference set of parameters for which we can use reweighting techniques to make this inexpensive, so that we don't have to actually run 1,000 different simulations. We, after the fact, can reweight to a bunch of different parameter sets to assess the uncertainty. But the data weights come in from the likelihood function. So whoever isn't familiar with the Bayesian statistics equality or prior, which is just some something that expresses your prior knowledge of these. Your posterior is what happens when you condition that on whatever data you have, and you can easily factor the data as long as the experiments are independent, statistically independent. So I measured this experimental observable on one day, and then I went to a different machine and measured this other experiment. On a different day, those are fully independent. So the data weight comes in expressing these guys, and I'll get to this in a second because it's really important for us to construct these models accurately. But the basic idea is that the more data you get in, the more kinds of data, the more certain you are about the parameters, and that means the more certain you are about predictions that use those parameters. And there's a way to actually quantify this using a concept that's called entropy. You may have heard of it in StatMech. It just basically quantifies how wide this distribution is. They also call this uncertainty, or in the information theoretic sense, and the entropy difference or the information content is how much does it reduce the uncertainty as you get a new piece of information. You can actually quantify that in the context of whatever information you have. There's a cool interactive demonstration. I'm not sure if this is going to work for Twitch, but
I guess my question was, can it also tell that no, you can't mix gas-phase data and liquid-phase data and get both?
That's a more complicated question because if you're unable to mix, you have to. Bayesian statistics assumes that, again, the hypothesis space is big enough to have a model that's transferable. If you have a fixed charge force field and it's not transferable between gas and liquid phases, then what will happen is that your uncertainty will be artificially narrowed, and you'll be misled about what it is that's happening. So you really do have to do this cross-validation of, if I train on one data set, is the solution, like the error bars might be very big, but at least the predictions for the other phase should fall within those error bars. And this is one of the questions of, can we automatically sort out which data sets are incompatible because they require physics that's not captured by the model.
So
I think that's something that we'll be able to figure out automatically.
Some of this is something we've actually been discussing the last couple of days in Slack. Is we were debating, like, should we really be using like heat of vaporization to parameterize to at all? So we said, well, we should really just be able to say, let's run the experiment where we don't include any data that involves transfer between gas and solution, fit a force field, and then try again with including that data and see if it makes transferability worse or better.
Or see if it makes results better on problems that we care about.
Yeah.
You can also simply take data class A and data class B, train on A, predict to B, and see if it totally violates your uncertainty, confident, or posterior predictive intervals. So this is just a simple example where we have a prior, and as we get more information, which you can control by this cool slider here, it reduces the likelihood, but doesn't change your prior. But that means that the product of those becomes more and more peaked, and eventually is dominated by all the data. So eventually you'll wipe out the prior. There's other cool things you can do in terms of hypothesis testing that I'll get to in a little bit. But the basic idea is that you have these things that quantify how wide your posterior predictive interval is. It's a bit similar to confidence intervals in normal statistics.
So the basic idea, concept there is that you start out with only the information you assumed beforehand. And if you gain a lot more information, that prior information mostly goes away because now you have all this new information. So rapidly switch over.
And we can encode whatever we want in these priors, right? It could be something that's, we usually try to strive for something that's not too biased, that's relatively information devoid. And there are certain properties of these where you may want them to be relatively invariant to how you parameterize things. Like if you have a torsion angle, reference torsion angle, or something that's an angular parameter, you want the angle and the cosine of that angle should give you the same posterior, right? You shouldn't change all your predictions just because you made a different parameterization of whatever it is, or x squared. Like they should give you the same sort of thing. So there's a family of priors that preserve this kind of metrization because it divides it out in some way. Jeffrey's priors are one example of those, but there's lots of others too.
So if you start with a bad prior, does it just take more data?
It takes a lot more data, but you'll eventually get there.
Right.
But unless you have a prior where you actually set it to 0.
Okay, 0.
Yeah.
Sure,
So we want to
why
avoid
not,
that.
Why not just do flat? What's the argument?
Flat is good, but
thing that
even flat depends upon for Leonard Jones, for example, do you take sigma or do you take log sigma as flat, right? One of them gives you a scale invariance, the other gives you just a flat over some number of angstroms, even though the hyperspace volume is changing a lot as you go. So there's questions about what you want it to be flat in. So I think informationless is more of the thing that we're striving for.
As long as it's non-zero everywhere, it's just an efficiency question.
But there's other things we can do too. If we did have information on the physical constraint, like sigma has to be positive, right?
Sure.
That's important. It probably is between some physical endpoint, like it's probably more than 0.1 angstroms and less than 10 angstroms, right? Those are other things that we could put in as constraints. We could also use prior rounds of inference. Like if we've done this already, we can actually use samples from a previous round of inference, and you can even do things like use your likelihood to reweight these on the fly. So you don't even need to do more parameterization if you have in-house data that you want to condition on. You can just do a reweighting of some of your predictions after the fact. So that's pretty cool too. And then there's often things where we'll have to introduce additional parameters because we don't know the noise characteristics of your ITC in your lab, for example. That might be a nuisance prior, but if we have enough data, it basically conditions that prior and we don't need to worry about it. We can just integrate it out and not worry about it. So those are the kinds of priors that we're looking at. Now, to come back to your question about likelihoods, a lot of our task is going to be engineering good likelihood functions to describe the data, and because that's where the data weights come from. That tells us about how we weight one data set versus another data set. As long as the data sets are compatible because our model space can actually describe the transferability, then what happens is that we'll need a forward model which describes how you relate the parameters theta to whatever it is you experimentally observe but is corrupted by noise after that. And then how you relate...
That just went by a little quickly for me.
So forward model is basically, I have parameters theta, so I have, let's say, Leonard-Jones sigma and epsilon for united atom methane. And then I have some model that says, what is the true density of this liquid if I was to run the simulation out for infinity, given those sigma and epsilon parameters. And that's something where we have to have best practices that describe what's the right way to compute whatever is going to be experimentally observed, assuming there was no experimental uncertainty or variability.
So really what you're saying is your forward model is like the recipe for calculating that thing.
Yes, essentially yes. And there's a lot of work, for example, on NMR observables by Michael Nilgas, for example, on how to, coming up with good forward models for NOEs, things like that. So there's things that we can leverage when we get to things like NMR.
Yeah.
For things like densities, it's pretty obvious, though. The question is, do you compute average N over average V for NPT ensembles or something like that? There's many ways to do this, and they converge with different rates, but they converge to the same thing in the thermodynamic limit. And then the experimental model is just describing what's the error model for whatever measurement we're assuming, because using something like ThermoML archive, we do have good estimates of what the variability is. Those might have to be corrected by NIST's assumptions about how likely experimentalists are to actually be forthcoming about all of the sources of error in their experiments. But then you might have something simple like a Gaussian that describes the deviations just from the experimental uncertainty. And this is what really drives the weights you're talking about. If you have a very precise measurement that we're really getting wrong, that data is going to contribute a lot more towards the likelihood than something that has a really horrible uncertainty, but we're getting very right.
Although, I'm saying things that people know, I guess, but that there could be other rationales for putting weights, which is like, I really don't care. I mean, it's nice to know that we get the properties of water correct at 500 Kelvin, but, and I may know them really, really well, but I don't want that to mean that it screws up my room temperature simulations.
Now, again, so this comes back to the question of whether or not our model space is capable of describing the entirety of the data space that we're putting in.
So we know it's not.
Right. So that's that practical thing we have to deal with. If it was capable of that, it would be no problem if we also added data at temperatures we don't care about.
But it only give us better physics.
I would say the argument is that if we think the model has a relatively restricted domain of applicability, we should restrict the filtering of what data we actually put in rather than try to weight it, because it's going to be much easier to just slice ThermoML for the pressure and temperature and chemical space we want than it is going to introduce data weights into a scheme that's Bayesian.
Can I give some example where I think data weights, that there needs to be some way to include it, and it could be that there's some way to include it in the prior. It's when you want to constrain to some property, but it's much less important that that property be right.
Exactly.
So maybe, this may not be physically quite right, we don't really need the density to be that close. However, the densities have extremely small error bars.
Right.
And so what we'd end up doing is we get the density very close, even though we don't need it right for the predictions we're interested in.
I mean, you can.
How do we?
This method is very similar to the regularized approach that Li Ping uses. So what you're doing is you're essentially describing what Li Ping is trying to do by enforcing. So there's a few different things here.
But it's true. There needs to be a way to include that idea.
I disagree, but there
Okay, good,
is a
because-
mechanism to do
Because
that,
every
right?
time we write a grant on this, people hammer us on
So
these details.
If you take the
Right.
logarithm of this, right, you get something that's like it's essentially a loss function, right? You have the logarithm of the likelihood because these are just products of things, and then you get something else that's like a regularization term. In Lieping's case, he restrains his parameters to be close to a reference parameter set, so they don't go crazy, which means that you can use less data and still get some improvement because you can't go too far wrong.
But that's
you can-
restraining the
So
parameters,
that's
not weighting the
So
data.
there's an analogy to each of these terms, right? So in this other case, there's two things that he has to weight the data for. One of which is the data has different scales, right? So in his case, he doesn't put in experimental uncertainties. He puts in something that has to do with scaling the data to a range that some people call this whitening, right? It's just making the variance about unity. And then there's another term that gets multiplied in there implicitly, which is how important is this to match, right? So that capability already exists within the force balance framework. So I think, and we've been talking about, we're going to start with that, right? So I think that's totally fine. Like if you can come up with a justification for...
I think that I think that there may be actually some interesting almost theoretical considerations here, and probably there are people who already know it all, but I mean, in a sense, we're using Bayes, we're talking about the likelihood of the parameters, right? We know the parameters are wrong because the physical model is wrong. So the parameters are never going to be perfectly likely. And so then the question is, how do you do Bayes correctly in a space where you know that you're never going to get the right model? And maybe there's a rationale for formalizing a concept of importance of what you care about more.
Possibly,
Or
right.
consistency.
Or things like that.
We have very different data with different physics, right?
Yeah,
so
yeah,
your uncertainties in the parameter is just going to increase.
No,
because
actually...
because the same physical model cannot explain both the...
It might apparently decrease in that case, which is wrong and problematic.
If the physics is different. Like, if one is 0 degrees Kelvin and another is 1000 degrees Kelvin, right? Trying to get water properties.
If your model is only capable of describing one of those phases, then adding more information is going to cause the uncertainty decrease, but incorrectly.
Increase compared to just doing water at room temperature.
No, but I think the point is that this goes to the fundamental question of using Bayes to test hypotheses where all the hypotheses are wrong because the force field is wrong. So if you say I want to fit to 1000 Kelvin and 10 Kelvin for water, you're going to get parameters that may be very tightly constrained, but they're going to suck when it comes to computing those the properties that you care about.
You had a point, Josh? I mean, we see this in the GV models.
Yes, if you go back to the previous slide where you define what you mean by, or one more previous slide, where you define the information gain. Maybe we need to revisit that and because what we're saying is we don't really care about how spread out our parameters really are. We care about how spread out our predictions are given the parameters. So if our model somehow doesn't really care where we are in this large chunk of parameter space, it gives us the same predictions each time for something we care about, like those guys find infinity, then maybe the information gains lower.
Well, you can also evaluate the information gain on, as you said, on predictions that have nothing, like if your data is density data, but you want to predict binding affinity data for host guest systems, then you can evaluate what the expected information gain is on those predictions for things you haven't even measured yet, given the information that you do have. So within the Bayesian framework, you can actually quantify how useful different pieces of information are, but that's still assuming that your model space is big enough. So you're saying maybe we should come up with a way to recast Bayesian statistics in a way that deals with the fact that my model space isn't big enough. I'm not sure that's possible. My approach is to instead
make sure we're answering the right questions. For example, for this, I could add in an arbitrary experimental measurement that for some reason had really, really, really high uncertainty, low uncertainty, which I could just do by measuring the heck.
And it could dominate the likelihood.
And it would dominate. And so we need a way to either binarily say that experiment shouldn't be used, or a way to say, well, it should be used, but it shouldn't be. There has to be.
But once you say that you're not using
arbitrarily screw up the results by including the wrong data.
Once you say you're not using some and you are using others, it is a weighting function. It's just 0 and 1.
Exactly.
So why not be general about it and have it?
I guess I'm still not convinced that there doesn't need to be a way, not just a likelihood, but saying how important the data is to again, it's how important the data is to the thing you are predicting.
Right.
So maybe it's a meta thing like that you need a meta statistical way to say what data to use and what not to use before you do the Bayesian, and that's how it comes.
Right.
So you're asking the right question.
The way I would do this is that I'd work on expanding my model space because that's the simplest way to improve accuracy, and B, actually ensure that the Bayesian method is more capable of quantifying what the true predictive
When you
uncertainty
say increase
is.
your model size, you mean use a more detailed force field in effect?
Possible, or at least
Or that
allow the possibility
Okay.
of more detailed. As we add in the possibility of point polarizability, right?
understand.
We become capable of describing transfer between two phases.
Okay.
And then you'd make sure that all the data is
So
compatible
I
in
have
the
a
sense
concern
that
here. Like, let's say if you had a nonlinear curve that has a linear regime that you're interested in, right? And if you start including data from this very nonlinear part, from this regime, that's not of interest to you, and you try to fit a linear model to it, right?
yeah, no, it's
So
obviously going to
uncertainty
fail,
in the
right?
slope is going to be high as you include the nonlinear part that is not of interest to the actual problem.
I don't think it would increase the uncertainty. I think it actually incorrectly
No,
decreases
because
the
you would have
uncertainty.
more points that you
But
cannot.
I wonder if I could just cut through this a little bit and say, whether or not it increases the uncertainty, it would lead to a model that was not where you
Is
wanted
more
to be.
incorrect,
I think
yes.
we could agree that.
Yeah,
we
yeah, yeah.
Okay, so
So no, this is a real concern, and this is why like the proper thing to do would be to increase your model space to allow more and more like a quadratic,
But, okay.
a quartic
That's
term.
But I think-
satisfactory
That's
because that
expanding
means
yeah,
that means that in theory we can't actually do this right with a fixed charge force field.
right. And I think maybe at a certain point maybe it's okay to be a little bit humanistic and maybe not have a wizard up there, but have a chemist up there who says these are the data that I care about,
Well,
and these
so,
are the data that you care about.
so I'm that's why
We can put
in
this up
mine
to-
I sort of
It's
framed this
interesting.
as
That's the result.
I think it's important.
I didn't say this very much, but the way I have been liking to think of it so far is the most of the argument we should be doing and the science we should be doing is about deciding what goes into the meat grinder.
Yes.
In other words, what data you put in and whether you really want to put the data in, that data in because, yeah, the density data is going to constrain your stuff a lot and maybe you don't want that. But I think once you put it in, you have to not be tweaking with weighting stuff because otherwise you can't automate it unless you sit there as a human expert. And we want to get rid of the human experts so that we can find out how much each type of data impacts them.
So just
And
to
other-
give you an idea, right now force balance, as I understand it, requires one manually selected parameter per force field parameter plus one manually selected weight for each measurement class. So that requires more human selected numbers than parameters you're fitting. So that this is something that we'd like to move, like we'd like to make as much of it parameter free as possible. And the only real easy way to do that is to make some decisions about what data classes to include because of what you're interested in, and then try to expand your model space in some
That's an
feasible
implicit
way.
It is, but
It's, yeah, but it's,
Which
it's
I'm
parameter
fine
free.
with. I'm fine with. It's just, it's not weight free. It's just we're moving all of the weighting decisions to some chemical to which it should be for. And once we do that, there's no more weights. That's totally fine. It's
So
just not
there may be an intermediate regime, but I don't know what that looks like.
Yeah.
So but even without the intermediate regime, there's still a ton of advantages, right? Like we're able to predict the posterior distributions and get uncertainties in whatever predictions we want. And so they're a little bit small, right? If you have a limited model space. Still, it's better than nothing. We're not saying that the bias is zero anymore. We're saying the bias is non-zero, and we can start to quantify it. And as the model space gets bigger, then we get a more accurate estimate of what that real error is. And so,
And this is the
and
kind of
we
thing one
approach
could
that
test.
asymptotically. Yeah.
This is the kind of thing you could test. Is
Yeah,
like, what do they
absolutely,
really
yeah,
look like?
yeah.
Okay.
And we can use this to, as I mentioned earlier, we can use this to determine whether certain data classes are incompatible because they just don't capture the force field can't capture the physics of transferability between those application domains.
Interesting.
So I think the benefits far outweigh the drawbacks of possibly being a little bit misled. Now there are some cases we're going to run into trouble, like the GBSA models that are just totally wrong, where the uncertainties look really, really small until we start allowing it to have more GB model class variants that are accessible to it. So I think that was my original finding a little while ago.
If you could tell me not to disrupt any further, do you want to go
Are we going to hear a bit more about the GBSA stuff tomorrow?
Yeah, or I think so.
Today, okay, yeah.
But I think this point that was just raised is really important. So David a few minutes ago was saying how the important question is what data we select to go in. But I think the point just raised shows that you chose an example of a horrible method,
Yeah.
GBSA.
Yeah.
In fact, there's going to be an interplay between what kind of model we're testing and the kind of data that has to go in, and that could be quite illuminating. I think of this myself just in terms of our valence angles, which are all harmonic.
Yes.
So you've got our ring systems which constrain those. Our harmonic bond angles, our general harmonic bond angles are going to be horrible. then when we include one which has more anharmonicity baked in, it'll be more flexible, so you'll be able to include that data without it going off the rails.
Mhm.
So I guess what I'm really trying to say here is, in the overall discussion, although I don't fully understand the details of this Bayesian method,
Mhm.
I do think that the importance of different kinds of data, whether we do it by weighting or by completely eliminating them, will have an important interplay with the models, and it will inform us about the size of what we're doing. And my 2 cents, if I'm going to come in, is I'm going to say it could be useful actually to have weighting. If you do it binary, include or exclude, then you only have a classification quality information informing your choice of model. If you use weighting, then as the weighting goes between 0 and 1, that can actually help tell you how good your model is.
So this is where, after protesting that I don't want to include weighting, I'm going to tell you how to include weighting. So we in the GBSA case, it's really not going to work at all unless you include some ability to handle the fact that the model is incapable of representing that particular experimental data class. And in this case, we took the simple approach of expanding the uncertainty by this other thing that says, here's the limitation of my model for this data class. So what that means is that whatever prior you put on that is going to be effectively your weighting. So we did something very simple, which is to say we don't even know the scale of the error and wanted to make it uniform in log sigma. But essentially, you can introduce your weighting in terms of priors for each data class in this case, depending upon how. So what this does is it tries to keep it small, but still not so small that it kills your likelihood, because you have all of this data that opposes that. So if you wanted to introduce weighting, here is how I would suggest to do it if I was covering my eyes. Does that sort of answer your question? So the prior is at the level of how much model error am I allowed to tolerate, or how do I penalize that at the level of a prior. So it's similar to a data class weight, but it's not quite the same.
Yes, my limited experience with Bayesian optimization is showing I will probably need to look at some direct examples. But I in principle, I see how it could help.
So I was mentioning that much of our effort is going to be focused on making likelihood models. So it's coming up with a good biophysical model or a physical model for how to compute something. We've already started, I think Bryce has been working on the best practices, and then what's the good experimental data model, which really involves understanding what the experimental error is. And we've been obsessed with this for things like isothermal titration calorimetry or NMR data or other kinds of things. And there's all of these data classes that we're going to have to deal with. David flashed these up. They inform different kinds of things in terms of our force field, which is why we want to include or exclude different sets of these. But coming up with data models for all of them, and then also the forward models and good error models for the experiments is something that is on our task list. David also mentioned ThermoML is a fantastic source of these. This was a few years ago, so it has more than 136,000 measurements right now. And it's something where we hope to automatically pull data sets we want by just slicing bits of this database, and then including whatever properties and whatever thermophysical temperature and pressure ranges we're interested in. So here is a very simple example that I think Levi put together with Michael, where if you have just density or just enthalpy, you're looking at the highly likely part of united atom methane space. So just density says there's this region over here of parameter space that gives you essentially equal fits to the data. Same thing with enthalpy. There's this weird squiggly line that gives you essentially equally good fits, but when you multiply them together, you get this conditioned, much smaller region of parameter space. And I think Alan Mark has been showing plots like this too, where you have these hypersurfaces of hydration-free energies that intersect. But the basic idea is that the more data, the more things are constrained. I mentioned quantifying the uncertainty, but you can also do model selection, which is a really important thing. Again, if your parameter space is big enough, and you can even have different models with different numbers of parameters, and you could say which one the data prefers more. So you can come up with something called the model evidence, which quantifies in a Bayesian gambling odds ratio, like how much evidence you have behind one model versus another model. So if I went to a gambling parlor and there were two different models that could have generated observed data, and the dealer is able to pick one model and generate data from it, you could actually, if you iterated this process, break even by gambling a spread on whatever the evidence ratio is. So there's a very nice gambling or Bayesian gambling interpretation of this. So it's the iterated betting odds on a spread. And you can also do this sort of thing. You can either compute these directly, which is exactly the same as computing ratios of partition functions, or you could include them in a single simulation. So there's a way to hop back and forth between discrete models in a way that satisfies detailed balance. Basically, if you wrote down detailed balance, this is exactly the expression that you would get. It's called reversible jump Monte Carlo, and it's a little bit complicated if your model spaces have different dimensions because you have to have some way to propose how to increase or decrease the number of dimensions. But this is the same thing as grand canonical Monte Carlos. Transfer of insertion of a new molecule comes with it more parameters, which describe the position and orientation of that molecule. So you're changing the number of degrees of freedom on the fly, but you do this in a way that satisfies detailed balance.
I think the key is that if you set up that detailed balance correctly, the time it spends in each model
The
is
fraction of time is the
Right.
same as it's proportional to this evidence. So what I mean here is that these are two things that we want to do, Bayesian model selection, and especially in the same simulation, we already know how to solve these problems.
And here, I mean, given that more parameters is going to make the model look better, you presumably have some chemical potential of adding a parameter.
The chemical potential is actually natural in a way that just like under equilibrium conditions, you don't have a phase goes all the way to the other phase. It comes to some sort of equilibrium that doesn't completely fill up generally.
But I guess basically what I'm saying is, how do you sort of what is it, regularize or normalize for the number of parameters?
It's natural from the way that the prior is constructed. So it penalizes complexity in a useful way. So if I was to just illustrate how this happens, suppose we had one atom type or two atom types for some liquid where essentially it was equivalent to a Leonard-Jones fluid where everything was a single atom type, epsilon and sigma, and say my prior was just flat over this region.
Right.
And in order to get good agreement with the experiment, I have to put them here in this tiny little circle which has area A, and this is, let's say, area B. So the prior is A over B, right? Now if I create a second atom type, and it has to also be in the same little tiny circle, then now my posterior is A over B again. So if this is a small number, now it's even smaller. So it penalizes complexity simply by the virtue of the fact that unless I had more than a B over A gain in likelihood, it's going to say, no, I don't want to do this. It's really favorable to have just one parameter that hits this.
Penalty entirely in the prior.
It's an entropic penalty that comes from having to confine your parameter space to this tiny little region in order to fit.
But
if I was able to split my, say my first parameter is here and my second parameter is over here, so now I could get, say, a B over A or more.
What's a B? I'm sorry, what's a B over A?
It's just a factor. Say this was the area ratio A over B is 100, 1 over 100 or something like that.
Oh,
So
B
it's
is the total box.
B is the total box size, yeah. So it's a tiny little hypervolume fraction of the box to get a good fit to the likelihood function. And say the likelihood is terrible everywhere except for this tiny little region. Now, if I had one parameter and that was good enough to fit everything, then I would get just A over B is the prior penalty. If I have two parameters and it still has to be in the same place, but it doesn't increase my likelihood at all, then it's going to be highly disfavored. But if it increases the likelihood by a factor of 100, now that cancels out exactly by this B over A term. So having the second parameter would be totally fine. Or it would be at least ambivalently preferred. If it was more than a factor of 100, then it would definitely prefer having two parameters.
No, I don't get it, but I'm probably should spend time on it. That's okay.
A simple analog to this, which is let's find how many Gaussian components are in this mixture. So it's a really nice, easy, tractable solution where if you simulate from a mixture of two Gaussians so that you see something that looks like this, and you ask how many Gaussians are there in this, it's for a given fixed number of components you can easily solve the Bayesian problem.
Okay.
You could also create this reversible jump or compute the evidence directly for different numbers of Gaussians and see that there's a clear peak in two Gaussians depending upon the configuration. If they're really close to each other, you can't really tell sometimes, but you'd see that like two Gaussians is preferred over 1, 2, 3, 4, etc. If this is your evidence for the number of Gaussians. I'll have to actually work out a notebook for that at some point. So there's a bunch of questions that we have that look exactly like this, though, right? So the easiest one is which mixing rule should I use for Leonard-Jones? Then there's the choice of functional form. Should I use an exponential 6? We think it's physically reasonable, but does the data really say that there's a preference for one or the other? Or which atom types, which we're going to hear about a little bit later. And then we've also been talking about QM derived charges. So you can choose choose a semi-empirical type method, and you can choose how many bond charge corrections or similar you want and what their values should be. And this could also be sampled in this way because they're discrete choices. We're going to hear more about this later, so I'm not going to talk about it. But the basic idea is that everything I've talked about here, so the other reason I prefer this is that I know how to solve all of these problems because that's what we do for our day job. Everything here is a complete analogy or analog with something in statistical inference. So the partition functions for us are normalizing constants or model evidences. These ratios are the Bayes factors. Physical properties are just expectations statistically, and entropy is the same thing in both sciences. So the great other thing is that all the algorithms are the same. So there's essentially the same algorithms in statistical inference exist in our field as well. There's things like particle filtering, which are like these Rosenbluth methods where you're doing chain growth. There's things like parallel tempering and serial tempering, which are even called the same thing. We have Wang-Landau, which is also present in statistical inference. The semi-grand Monte Carlo is just the reversible jump stuff. So essentially, this book is a good way to get started because it unifies all of these within the same mathematical framework. So you could just read through all of the algorithms from both fields. Mentioned the challenges. Okay, so the other big challenge is that it's expensive, right? Every time we have to evaluate the likelihood function, first of all, it's noisy because we only have an estimate up to statistical error. And second of all, it's really expensive to run a new simulation and converge something like a free energy of binding or to less so a density. These things are quite expensive. So we have to come up with some sort of actual scheme that will allow us to compute the likelihood in a way that is not super expensive, so we can do some sort of sampling there. And we've come up with a way of doing this through several different levels where you start at the top and you query whatever oracle might have this information essentially cached through something like a simple surrogate model. If the surrogate model says that, okay, I'm too uncertain about what this actual likelihood value should be, I have to call down to the next level where I then look at whatever data I already have stored in some database or on disk, and if I can, I'll reweight to the new parameter set based upon the nearby parameter sets I've already collected data from. And if that's too uncertain, then I have to go back and actually do more simulation. But there's a very simple way to set up all of this. We were talking with somebody named Theo Theo Karaletsos, who's now at Uber Labs. They have a really cool probabilistic programming language called Pyro, yeah, that we might be able to use for this too. Huh. But he called this amortized inference, where you're basically saying, I'm going to punt on actually doing more work unless I have to. Think of it as lazy instantiation as well. But we can set up an easy hierarchy like this where every time we have to go down a level, it costs 1,000 times more. And we have to worry about exactly how we do this because we want it to behave in just the right way. So the basic idea is that you start somewhere, you've collected some simulation data, and you can say something using reweighting about some region nearby, but as soon as you leave that trust region, you have to do more simulation. Then that expands the region of parameter space where you have more information. So you take more and more steps, then eventually we get to the same region. We're still stuck there because this is the high probability region. We have enough coverage to be able to say something useful about this from just reweighting alone.
Is the trust region defined on the input or output? Is it like you always want to stay within a KT so that you can apply perturbations, or do you apply on the parameter?
It's related to the KT energy, but it's basically we were originally thinking that we want the prediction uncertainty, so you get a statistical error, which is in the prediction. That should be smaller than the error in the actual experiment. By probably an order of magnitude, in order for this noisy oracle that you're evaluating for the likelihood function to not be totally corrupted. So that we're still not sure what the ramifications are. There's other techniques that might allow us to actually deal with the fact that that's noisy, especially if it's unbiased. But
you can see how near the end of the convergence, you do want your.
Yeah, I guess I'm asking, well, how do you
but
define
near the
trust?
beginning, we do need some ways to be able to rapidly move towards the right regions without pushing down the uncertainty really over every single. Because if they're comparable size, and the likelihood is really bad, we know we shouldn't be there. We don't need to keep on drilling.
This is also a case for using a more traditional optimization context to start off with. But then this also, there are schemes that will get us over barriers because a local optimization parameter space is probably not going to get us very far. It's probably very rugged. So in fact, it's probably the same or harder as all of the problems we're used to dealing with, right? There's many local minima that such that any sort of sampling scheme is going to have slow mixing problems, so we're going to need to use enhanced sampling approaches. It's also of high dimension. Smirnov, I think, it has 300 lines-ish. Is that right? So there's about 600 parameters right now, which is still really small, but it's a lot of parameters for any sort of optimization technique. Small compared to our biomolecular problems. It's likely to have some really ill-behaved regions when you get to like epsilon near 0 or weird sigmas, where things might just blow up or become ill-behaved. And it has highly varying scales. Like it's at some point you can't really change some of these parameters by more than a fraction of a percent, whereas others are very tolerant to changing them by, possibly even an order of magnitude. So these are just based on intuition here, but probably need something adaptive to handle the scale differences so that it knows what the different dimensions, how they differ and how to handle those. The gradient information probably offers a lot of information. I think you've used gradient information before in optimizing host-guest.
Yeah, we're going to talk. I'll talk about it this afternoon.
Yeah, and that's
James.
presumably much better than just using Monte Carlo.
So, I mean, just on this slide where you're laying out the problem, we're getting down to practicalities here. Knowing that many of these degrees of freedom are really, really what I call tight or hard degrees of freedom, like bond lengths, and then most of the issues where it's really expensive to run like a density calculation. That's where you're looking at the tails of a relatively few parameters, like a dozen parameters in the 600. So doesn't this naturally lend itself to some kind of a hierarchical model where we're only going to ask the question like, do we need to run another density calculation, not to test the carbon-carbon bond length?
Yeah, so that's something that's built into all of these algorithms, right? Even simple things that we've been using for GBSA, like PyMC, allow you to say, okay, for this molecule, if I'm updating say a hydrogen connected to a oxygen, right? I don't need to recalculate any parts of the likelihood that don't involve that atom type. So I can already structure my calculation in a way that makes the most use of reuse of existing data where I don't need to change anything. So,
but I mean that's I would say a trivial example where you can a priori say if this parameter isn't even being used, we don't have to test it.
Right.
But do we need to run a density calculation on ethanol to test the carbon-carbon single bond when there is a carbon-carbon single bond in ethanol, but it's just really tight. There's no need to do. See what I mean?
But that will be automatically handled by a scheme like this. Like if the symbol models are confident that it's just not going to matter, then it won't even go down to the next stage.
So it will naturally fall out at that level.
Yeah.
We will see that the surrogate model says this is trivial. There's absolutely no need.
Or MBAR says that there's no error here. Like
so that all naturally shakes out. Okay.
So I think that's the way we structure it. And this could be more levels too. We can come up with as many as we like, as long as we structure things in the right way. The good news is that our timeline has left us lots of time to actually get this infrastructure working, and we don't have to start integrating these until much later. This is sort of our initial proposal for essentially a 2-year effort, where at some point the Bayesian torsion fitting is going to be the most important to get working, which Haya has been working on a little bit, and then then we need to refit things like Leonard-Jones. The best way to structure this is really to use a staged approach where we ask one question at a time and peel off bite-sized chunks. And each of these can also lead to papers, which is very useful. So for fitting the GBSA parameters, for example, is a really great test system because we know that the models are wrong. And we also can really easily evaluate the likelihood function because it's super fast. There's only about 10 parameters as well. And then we can also check a few discrete models to see how that expands the model space. So I think that's a really useful way to start this. And so Bryce and Josh have been working on that. Haya has been working on torsion fitting because that's a more straightforward approach where we know that the main issues are just overcoming the degeneracy problem and the multiple minima problem to come up with good torsions. If you're controlling how many different torsion periodicities you have, then you can also have this other problem of I need to switch terms on and off. So you have a discrete optimization problem coupled to your continuous optimization problem. That's something that Haya has spent a lot of time thinking about as well. Leonard-Jones only has about 36 parameters in Smirnov right now, so that's another great thing that would give us a huge increase in accuracy. But then we have to worry about the fact that we are refitting very expensive data, but it's not as expensive as binding affinities. So it's an intermediate step.
And the Leonard-Jones data, I mean, those impact the torsion fitting through the 1.4s, presumably? Yeah.
And so all of these are designed to be modular. So with the idea that the torsion fitting already removes everything else from the rest of the force field. And if you have enough, then it's supposed to be somewhat generalizable, but that's still an open question.
But
We would then be able to couple them together, right? So in the context of some of either a torsion fitting framework, we could then refit the Leonard-Jones with that going out at the same
So sort
time.
of like each time we do something, we automate it. So like when we refit the LJ, we also refit the torsions again.
Yeah.
So we
Okay,
automate
okay,
it.
so
Yeah,
we're
yeah,
done
but
in
they're
tandem.
all meant to be coupled into the same framework.
Cool.
And that's when things become hairy from the software development point of view.
It's actually not too bad. I mean, a lot of optimization approaches have kind of like this inner and outer sphere, where like you optimize one set of parameters and you optimize the inner set, go back to the outer set, flip back and forth.
Right.
It's very common, and that's completely hierarchical. So I mean, you can even have one more level to that.
Mhm.
Because like what you do is because you keep this so small, and like you know that within like a certain framework, LJ is going to be you can actually solve that via least squares in like one iteration, so it's not a loop. So you can just do these big macro cycles.
Yeah, I think there's a lot of strategies that make it easy to couple these together, and also some of these are super fast. Like the likelihood functions are very fast to evaluate compared to
Right.
these more expensive ones, which require simulation or inference.
Right.
Just to make sure it's clear to everybody, refitting LJ will be something like, okay, I make, let's say, a Monte Carlo move to my parameters, and then I have to evaluate how likely my new parameter choice is by computing the density of a whole bunch of things,
and enthalpies and
enthalpies, and so on and so forth.
mixtures.
So each Monte Carlo move potentially involves simulations.
Whereas the
Which
torsion,
is the hierarchical one.
Yeah.
whereas the
You mentioned
torsion,
that, I'll talk more about it.
whereas the
torsion-
torsion's just comparing with some quantum data, presumably. Yeah.
Where there are also challenges about now we don't have any idea of how accurate that information is. So that's another challenge for the Bayesian approach, is that how do you deal with that not having any idea? So we've put a nuisance parameter on how accurate we think QM is. And by coupling it to Leonard-Jones, suddenly you're using physical data to inform us how accurate the QM profiles are, which is somewhat interesting. And then things like which Leonard-Jones mixing rule should we use? Now we have a few discrete choices that also involve the same kind of calculations. We've been prototyping this a little bit with sampling over GBSA types, so that's going to very much take advantage of the framework that Caitlin has been working on. And then finally, you can start to get into selection of which non-bonded functional form do you want. Do you want to use exponential 6? Do you want to use Morse potential or something else? You can even start to add higher order terms onto Leonard-Jones, like add 1 over r to the 8th, 1 over r to the 10th, things like that as well.
You've looked at charges here, so.
That's the next page.
Okay.
So then it gets more complicated because now we start to talk about non-bonded typing, like how many non-bonded types do we need, and we're starting to create and destroy types there. Same thing with the electrostatic model selection, choosing some sort of semi-empirical scheme, and then which bond charge corrections you want, because now you have a mixed, continuous, and discrete optimization problem. And then finally, like designing these liquid mixture experiments where you can start to use the power of Bayesian experimental design to say, you should go out and now collect targeted data sets that will inform future experiments too. So this is getting to later stage things, but they're all bite-sized pieces that in principle can have publications and inform what we do for the rest of the projects as well. And so how we actually are going to do this, we sort of need a way to exploit lazy evaluation to only call down each one of these levels as we need to. And what we really need is a very clear and simple API that lets us decouple this entirely from all the stuff that's going on with parameter optimization, either through force balance or sampling from posteriors using fancy advanced samplers that Josh and Bryce are working on. And so you need an estimator for each one of these levels that has a very simple, consistent API that can plug in such that it knows that what it needs to do when it can't answer the question itself is to just call down one more level, gather some more data, and then it can figure out how to incorporate that back into its own model. And so we've been thinking about having parameter sampler with a very simple API of a property estimator that's used to actually do the sampling. It has to do things like make sure that the gradient information can be captured. It probably has to stage things in batches too, to avoid the fact that if you have to do a new simulation for one parameter and then you realize there's 400 other parameters that also need new simulations, you should probably do them all at the same time rather than waiting sequentially for one to finish, right? So we either have to make this asynchronous or use some sort of batching scheme to get all the information at once to do, because we can exploit parallelism in the cloud or on our own computational resources very easily. I have just a very brief I don't want to go over time too much. What's the
So you
schedule?
also have talk
Yes.
after coffee break on timeline. So
Great, perfect. Okay, so I was just going to basically lay out our philosophy for torsions, but maybe we want to talk more about the torsions a little bit later because Christopher has some insight as to how we might want to adjust this plan. This was sort of just what we had proposed to Pfizer, for example, that we wanted to build a tool that had the ability to fit Bayesian torsions for a single molecule with the idea of scaling that up to many, many torsions at the same time. And the basic idea was if we have some way of taking small molecules and fragmenting them, and I think Haya has some slides she sent on that, making all of this in a giant QM database that can store lots of things, and then learning using machine learning to figure out where the gaps in this are, then we can start to actually figure out what we need to calculate to scale this up, and then learn from this in a Bayesian way. And all I had was here are 2 books that are really great to either wrestle with the theory or with the algorithms of what we're trying to be doing. So I'll make sure all of this gets online too.
So that one, there is a PDF of most of it online.
E.T. James? Oh, really?
At least there used to be.
So this was finished after his death by his student Larry Brethorst, who's done a huge amount of Maxent and Bayesian inference for NMR.
We had a book club on this way back when I was in Maryland.
Oh, fantastic.
A bunch of us worked through about the first third of it, which was...
It's really entertaining.
Yeah, but there are places where you can get hung up. I certainly got hung up, and the group discussion was... I'll see if I can find the PDF.
Cool.
questions at this point before we break for
I have it. You got it. Maybe you can post it on the... Okay.
So I think, this is there's going to be plenty of opportunity for discussion. So if you're not understanding something, this is your opportunity to pin John down and to explain it to you at the whiteboard or whatever. So harass him for that if you need. Or Josh. He's our Bayesian expert. So should we break for coffee and other refreshments?
It'd start up at what time?
It's supposed to be in about 15, 20 minutes.
Okay.
Great, perfect.
Cool. This stuff is maturing.